Okay, welcome to looking at trig applications. So this chapter is going to look at a whole bunch of different applications involving trig. We're going to start out by reviewing the sine and cos curve, sketching them, what they look like, and then branching into the reciprocals, and then doing some solving of trig equations and applying rates of change. That'll take place over the next 4 or 5 video lessons. So the first thing that we're going to take a look at is our common kind of curve, y equals sine of theta. I've drawn a little grid here. I've put everything already in radians, but I'm going to use this approach of creating a table of values. Now the table of values is actually going to come from the unit circle example. So I'm just going to jot down here the coordinate points of the unit circle, and we're going to use those to help us draw our graph. And then from this point on, we will need to be able to understand what they are. So I'm going to start at 0. So when theta is 0, which is 0 degrees, the value of sine, which is the second coordinate point, is also 0. When theta is pi over 2, which is 90 degrees, the value of sine of theta is 1. And we can continue this looking at all of the critical points moving around the unit circle. So pi will give us a value of 0 as well. 3 pi over 2 will give us a value of -1. And finally 2 pi will give us a value back at 0. So we're going to plot these points showing each of these where that's 1 and that's -1, and we end up at 4 pi over 2 or 2 pi. And so we would just do a quick sketch of our curve, and there is the graph y equals sine of theta. Now I left this as pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, but keep in mind that 2 pi over 2 is really pi, and 4 pi over 2 is 2 pi. This is just to show you that we're increasing each of these by 90 degrees or pi over 2. The second graph we're going to take a look at, we're not going to use the table of values. We're going to just recall what our cosine looks like. So if we look at the unit circle, we know that when cos of theta and theta is equal to 0, the value of cos is 1. At pi over 2, we're at 0. At 2 pi over 2, we're at -1. 3 pi over 2, we're at 0, and we finish where we started, which is back up at 1. So the cosine curve looks something like this for one cycle. Now keep in mind it does continue and travel all the way down and all the way back up and finishing up near the top. And the same thing with this graph, it travels all the way down. So it is continuous, the domain is infinite. The range, on the other hand, only goes as high as 1 and as low as -1. So there is the graph y equals cos of theta. So let's take a look at how we might graph a cosine graph that has some manipulation to it. So remembering transformations, we know that the 2 out in front here is going to act as a vertical stretch, and the +1 is going to be a vertical shift of up 1. If we're looking at y equals 2 cos x plus 1, here are some helpful steps that might allow us to plot this. The first thing is to find the d value, or what we call the midline. The d value in this case is 1. That's how much our graph has been shifted up. So the first thing that I'm going to do is I'm actually going to use this line that's here, and I'm going to show it moving up 1 unit. So this is called the midline. The next value to pull out is the amplitude, and the amplitude in this case is 2. That's our vertical stretch. The amplitude helps us to find our max and our min. So I'm going to use some dotted lines here, and from the midline I'm going to go up 1, 2 to get to my max point, and I'm going to go down to 1, 2 to get to my min point. I'm just going to move this line so it's a little bit more. And then I'm going to go back and I'm going to label. So this was at 1, this is at 3, and this is at -1. Again, amplitude is the distance from the midline to the max, or the distance from the midline to the min. So D and A are usually the first two things that we pull out. Then the next thing is to locate or find the period. Now the period in this case is found by taking 2 pi, which is radians, divided by our b, or some textbooks call this the k value, and that's the value in front of x. Right now it has a value of 1. So the period in our case is 2 pi divided by 1, or just simply 2 pi. Now this tells us that our sketch is going to repeat itself every 2 pi, or 360 degrees. We also use 2 pi to help us find the intervals to set along the x-axis, along here. I've got them hidden behind here. But the way we find our intervals is we always take the period and we divide it by 4. So in this particular case, it is 2 pi divided by 4, which reduces to pi over 2. So every 90 degrees, we are going to have a little tick or something along our midline here. So here are the values. Pi over 2, we'll just move that back up, would be right here. 2 pi over 2, 3 pi over 2, 4 pi over 2, and so we see the same values appear on the left-hand side. So if I'm just going to temporarily put a little tick here, a little tick there, just to show that each of these values are what they are. The last thing to take a look at is the horizontal shift, and in this particular question there is no horizontal shift, so there's no what we call a C value. So that's fine. So this means that the graph is going to start at the maximum point, which in this particular case is 3, because our cosine starts at a max if it's positive. If it's negative, it would start at its min. And then the rest of it is knowing that the critical points, the next critical point goes 90 degrees, which is through the midline, and then the next point is at pi, moving down to -1, which is our min, then back up to our mid, and then finally finishing where we started. And so here is the graph of, or sketch of, y equals 2 cos x plus 1. Practice those steps. Step 1, find the midline. Step 2, find the amplitude. Put a little dotted line here, which you can then erase afterwards. That's perfectly fine. But what the dotted line tells us is that our graph is only going to fall between those two dotted lines. Then we found the period by actually locating the b value, which is the value in front of x, and we divided that into 2 pi. Once we found the period, which is how long it takes for this graph to repeat itself, we divided by 4 to find the interval. We then went at the very last step to find out if there's a horizontal shift, which there wasn't, and so we went ahead and sketched. Now we have a word problem, so we're going to take our knowledge and answer some of the questions. So, an octopus ride in an amusement park completes 1 revolution every 60 seconds. So that means that the period is equal to 60, 1 revolution. So that means on a normal sort of ride that is circular, it will take 60 seconds to get back to its original spot. So that is the period. The cars reach a maximum of 4 meters above the ground. So now I'm just going to do a little sketch here. I'm going to say, okay, well, it's going to be 4 meters above the ground, and the minimum, it says, is 1 meter above the ground. Well, that makes sense because we don't want our ride hitting the ground. That wouldn't be a lot of fun. And that's pretty much the information that it gives us. It also tells us that they want us to model this as a sine function. So it asks us basically a whole bunch of questions that set us up nicely to do this. Question D is really the big question. Write an equation and do a quick sketch. So to do that, we're going to use those steps we used before, a little different order. This time it asks us amplitude. Well, amplitude is the distance from the midline to the max point. So it's kind of that halfway point right here. So if that's the midline, the amplitude is this distance here. So how do we figure that out? Well, we can take the max point and subtract the min point and divide by 2. This should give us the amplitude. So 3 divided by 2 is 1.5. So the amplitude is found by taking the max minus the min, dividing by 2. And in this particular case, it's 1.5 meters. determine the vertical translation. So this is also found by taking max and min, but this time we're taking max plus the min and dividing by 2. So in this case, the max is 4 plus 1 divided by 2, which is 2.5 meters. So this is the midline right here, running through the center. The desired period, well, we stated that originally. That's going to be 60 seconds. So the equation now has to fill all of these critical bits of information. So here we go. So I'm going to write over here that the amplitude, which is the A value, is 1.5. The D value, which is our midline, is equal to 2.5. I don't really need the units here. The B value, so the B value, if you think of the original equation, it's y equals A. In this case, it's sine of B x minus C plus D. So the B could be a K, the D and C could be switched, but notice the position of them, where they're located. So we have the midline, we have the amplitude. We're now trying to find the B value. Well, if you recall, that period is equal to 2 pi divided by B. Well, we do know the period. It was 60. So if we go and solve for B, we end up with B is equal to 2 pi over 60. And we could get that by cross multiplication and then solving for B. Well, as an exact value, we're going to determine that that's a pi over 30. So the B value is in fact pi over 30. Now, I don't think it says in the question where the ride starts, where we get on the ride. So we're going to assume, like most rides, that we would get on at the bottom of this ride. So if we do that, then imagine that we're going up and down, over and over. Well, this is helpful because this is the negative cosine curve from here to here. And then it repeats itself over and over. So the only difference is we can't use cos because it actually asks for sine. So what we need to do is we need to figure out where this graph crosses the midline first. And that will be found by taking the period, and remember our interval. To find the intervals, we take the period and divide by 4. So in this case it's 60 divided by 4, or roughly every 15 seconds. So from a sine curve, we are going to have a little bit of a shift to the right of 15 seconds. We'll do a better sketch of this in a moment. So here's what we know. Y is equal to 1.5 sine. The B value we determined was pi over 30. And then I'm going to use some brackets here. X minus 15 plus 2.5. Now remember, because we're shifting, that's a 15. Because we're shifting to the right, it is negative. So this is what the sketch looks like if we're just sketching this from the beginning now. So the first thing I do is draw my midline, which is going to be right here. And that's at 2.5. Then I'm going to draw some dotted lines that are up 1.5, so that's going to be at 4, and then down here just above at 1. And you want to try and space these out so they look as equivalent as possible. So that's going to be at 4, and that's going to be at 1. The intervals along here are set every 15 seconds apart. 15, 30, 45, 60, and 75, and this continues on forever. And because this is a cosine curve, I know that it's going to start down here, but we're going to represent it as a sine function that's been translated. So this point is going to go at 15, up at 30, down at 45, back down to the min, and then finish. So here is the curve that I've stated right here. even though we actually are getting on the ride here, this line does extend back here, and then it does extend all the way along, and this continues on forever and ever and ever. So we label all of our lines. So if we were talking about this, this was the height off the ground, and this was the time in seconds. The last thing we're going to do is take a look at the tan curve. Now, in order to do the tan curve, I am going to recognize that tan is the same thing as sine over cos. Now, anytime I'm dealing with a ratio, there are going to be restrictions. So I have to take a look and find out where cos of theta is equal to 0. And the reason is because anything over 0 is undefined. And if it's undefined, it means that there's a vertical asymptote there. So if I just very quickly sketch the cosine curve, I have something that looks like that. It's 0 here, and it's 0 here. What that tells me is that I have a vertical asymptote at pi over 2 and at 3 pi over 2. And if I continue that pattern, every 180 degrees. Now, what does our graph look like? Well, if you start to plug in some values, you can determine kind of what this graph is going to look like. I'm going to take out this graph right here because I don't need it anymore. So, the one thing that we do know is that the tan curve, when it has a value of 0, so think of where the graph is, it also has a y value of 0, and you can remember that from the unit circle. So right over here at angle 0, the coordinate point is 1, 0. Well, that's sine over cos. 0 over 1 is 0. And then it is also 0 here, it's also 0 here, and every 180 degrees. Now the question is, what's happening as we move around in this area? We know we can't cross these vertical asymptotes. So what I'd suggest you do is you do some test points. So let's take a look as theta approaches 0 from the right. So remember, a little positive sign over here means from the right. Well, if you plug that into your calculator and plug in the tan of 1 degree, you are going to get it heading very, very close to this number. So let's take a look at what happens with theta as it approaches pi over 2 from the left. Well, as you plug in values like 89 degrees or 89.999, you get an incredibly high value way up here. And as you plug in values close to negative 90 degrees, like negative 89, you get a very large negative number. And this would continue giving the shape that looks something like this. And you would have this tan shape repeating itself over and over and over again. Asymptotes are every 180 degrees. Points hitting the origin would be located every 100 degrees starting at 0.